let's go over the notes for Chapter 8. In Chapter 8, we will first review some of the material and technology used for Chapter 1. We mentioned in Chapter 1 that a population represents all possible outcomes or measurements of interest, while a sample is a subset of the population. If a sample is selected properly and the data from the sample is collected correctly, we can use this information to make a very accurate assessment of the entire population. Probability sampling describes the process that each member in the population has a known non-zero chance of being selected for a sample. The 4 probability sampling techniques are defined as follows. We have the simple random sample, which is a sample in which every member of the population to be part of the sample. Systematic sampling involves selecting every kth, which means every third, every fifth, every 10th, every 20th. That's what K stands for, a specific number of the population to be part of your sample. One concern about systematic sampling is periodicity, which is a pattern in the population that is consistent with the value of K. In stratified sampling, we divide the population into mutually exclusive groups, or strata, otherwise called, and randomly sample from each of these groups, Cluster sampling involves dividing the population into mutually exclusive groups, or clusters, and then selecting a simple random sample from these clusters to form a final sample. Now, non-probability sampling refers to a sampling practice that the probability of a population member being selected for the sample is not known. Convenience sampling is a type of non-probability sampling that is used when members of the population are chosen to become part of the sample simply because they are easily accessible. The most common type of convenience sampling is an internet poll. Now, parameters are numeric characteristics that derive from a population. Mean or median would be an example. Statistics are values that are calculated from a sample, such as the mean or the median. The difference between a statistic and a parameter is known as the sampling error. In general, we expect larger sample size to provide smaller corresponding sampling errors. The higher basically your sample, the higher the number of your sample, the sample size, the more accurate the results. That means the less the corresponding sampling error. The sampling distribution of the mean describes the pattern that sample averages tend to take on when randomly drawn from a population. The properties of sampling distribution of the sample means are the following. Once again, when we talk about the sampling distribution, is basically the distribution of means of multiple samples taken from a population. We need to know the properties very, very well. The mean of the sample means we use the symbol mu x bar is equal to the population mean mu, so mu x bar is equal to mu. The standard deviation of the sample means sigma x bar, or otherwise called the standard error of the mean, is equal to the standard deviation over the square root of the sample size. So once again, 2 main properties of the sampling distribution. Mu x bar is equal to mu. Sigma x bar, which is also called the standard error of the mean, is equal to sigma over square root of n. Let's look at this example. The average age of cars and light trucks in the US is 10.8 years. We assume that the standard deviation for this population is 3.7. A sample of 35 randomly selected vehicles was selected. Calculate the mean of the sample means and the standard error. Based on the fact that we have sampling distribution, we know that the mu x bar, the mean of the sampling distribution, the mean of the sample means, will be equal to the population mean, which in this case is equal to 10.8. The standard error of the mean will be equal to sigma over square root of n. Sigma in this case is 3.7 over square root of 35, which is n. Therefore, the standard error of the mean will be 0.6254. Now, when we talk about the central limit theorem, the central limit theorem states that for any population distribution, the sample means will be normally distributed if the samples are large enough, and by large enough we mean at least 30 and above. And when a sample size is large, the standard error is deducted, which results in the sample means have more of a tendency to crowd around the mean of the distribution. So, once again, as far as the central limit theorem, I want you to remember that this theorem basically states when we can assume normal distribution for the sampling distribution. I want you to remember that a sampling distribution will follow normal distribution when we have sample size of at least 30, or when we know that the samples came from a population that follows normal distribution. One or the other has to occur in order to assume normal distribution for the sampling distribution. The formula for the z-score for the sampling distribution is x bar minus mu x bar over sigma divided by square root of n. Sigma divided by square root of n makes the sigma x bar, the standard error of the mean. Since we have normal distribution, we will be using the same way to calculate the probability distributions as we did in the previous chapter. Let's look at this example. According to Strategic Vision, the average age of Mercedes buyers in the US is 55 years old. Assume that the standard deviation for the age of the buyers is 8.5. A random sample of 38 Mercedes buyers was selected. What is the probability that the average age of these buyers is less than 56 years old? Less than 56 years old. So we have the mean 54, standard deviation is 8.5, sample size is 38. So we have mu, sigma, and n, basically. And we want to find the calculation that x bar is less than 56. So, normal distribution with mu x bar equal to mu, which is 54. 56 is to the right. I'm looking for the probability of x bar to be less than 56. That means I'm looking for the whole area to the left of 56. Now, the z-score, 56 minus 54 over sigma divided by square root of n, not sigma. So pay attention, do not get confused with the previous example, with the previous chapter. In our case, for the z-score for the sampling distribution, we divide x minus mu with sigma over square root of n, not just sigma. So if we do the calculations, we will get 1.4505. We always round to the second decimal because this is where our table goes up to. So in this case, 1.45, 1.45, 0.4265, 0.4265. 0.4265 is the area from 54 to 56. I'm looking for the whole thing. I simply add the 0.5 on the other side, and the probability that I'm looking for will be 0.9265. A coffee machine dispenses normally distributed amounts of coffee with a mean of 12 ounces and a standard deviation of 0.2 ounce. If a sample of 9 cups is selected, find the probability that the mean of the sample will be more than 12.1 ounces. Even though our sample size is less than 30, it is stated that the population follows normal distribution. So in this case, based on the central limit theorem, the sample size becomes irrelevant. So that means that our sampling distribution follows normal distribution. I'm looking for this probability where x bar is greater than 12.1. Mu x bar is the same as mu 12. 12.1 is to the right, greater than 12.1. I'm looking for a right tail. We calculate the z-score when we do the calculations for the z-score, and again, make sure that you use parentheses when you do your calculations for the z-score for the sampling distribution. The z-score is 1.5. 1.5 corresponds to 0.4332. Since I'm looking for a tail, I will have to subtract from 0.5. So 0.5 minus 0.4332 is equal to 0.0668, which is the answer. So this concludes the notes for Chapter 8.